So from China Academy of Science, Lei Yang, who will present the Chinese ADS prototypes and apparently some new developments with granular type of layout. So please speak.
So now it's
it's
open.
You have the floor.
Yeah,
yes.
okay.
Please, could you advance?
Yeah, okay. Yeah, point. So this is, yeah, okay. It's the laser. Okay. Good morning. Here I give a brief report about current state of the Chinese ADS project, and I come from the Institute of Modern Physics, Chinese Academy of Science. And from the 2000 to the 2010, China has a small project. I think it's just $100 million, the budget for the conceptual study, for example, by the CIAE and CAS. And one thing is Venus. Venus is for the zero-point blanket test, and another is for the RFQ, but it's running in a post beam. Okay. Then in the 2010, we have hold several meetings for the international how to say, consulting this project. Then in the 2010, we begin the some bigger project. Then this is a Chinese ADS roadmap now. We have 3 phases, we think. One is the initial felicity, another is a research, and then is a demo things. And now we think the parameter for the initial felicity is for the proton beam is 215 MeV and the 10 milliamps, and the total power, thermal power of the blanket is 5 to 10 megawatts, like this kind of things. Okay, it's also a duplicate front-end injector for the accelerator, and it would be finished the commission in this year. And the whole initial felicity, I hope it could be finished in this year. And for the accelerator, for example, we have a 2 injector and we have a 2 frequencies of the accelerator. For example, the injector 2, now we are begin to the CW continue wave mode testing from the middle of this year, and it includes ECR, LEBT, and RFQ. And this is a picture. And we have finished several fabrication for the HWR superconducting cavity, and finished the last year finished the vertical measurement and the copper for the HWR, and this year we have finished the high power testing. And then is the fabrication for the spoke cavity, superconductivity spoke cavity, and this is our design for the cryo module, and now we are begin to do some testing for the cryo module. And now we have began to build our commissioning hall. This is a design, and this is a picture. And next year, we will begin to commission the ECR and LEBT, RFQ, MEBT, and one CRAM module, include 6 HWR superconductivity cavity, and then the beam diagnosis system. And this would be testing in next year, begin to the next year. So this is a layout of the accelerator for CADS. This is a beam dynamic design has finished for the 10 milliamps, and we have a 2 design of the injector, front-end injector. One is the high frequency and half frequency, and is same frequency with the main Linux. And this part will be finished in the in 4 years. And this is a different task because whole this is separated the study by the IMP, CAS, and IHIP. Then is the reactor. So 3 years ago, when we consulting by the international teams, colleagues, then the LB reactor is how to say, we think is since we are beginner, so that is a very optional choice. So this is a design for the LBE reactor, and this is a geometry size of the, for example, the core and some vessels and these kind of things. And then this is a hydraulic, thermohydraulic, and include the passive resident heat removal system. And this is a calculation for the core flow distribution, and this is some CFD simulation. And this system is only total thermal total thermal power is only the 5 megawatts, so the average linear power density is quite lower. It's just nearly 4 kilowatts per meters. So we used a natural convection system. Then it do not need a pump. And then is mechanics analysis and some refueling system design and shielding design. And for the target, we have a separate LB target is have a 6 meters high, and we do some how to say, integral CFD calculation, include the beam deposition, the temperature, and the hydrodynamics, and the structure analysis, and all these things. But this target for now design can only working in the for the beam current is the 2 milliamps. And this is neutronics and some heat exchanger and beam windows design. And then we have finished our testing loops for the LB system. It be built in Hefei, the INEST Institute in CAS. And this system has this is building for this test loops. They include many loops, and for example, they have natural convection loops higher, taller than the 10 meters high, and this loops designed for the maximum temperature test is 800 degree, and max velocity is can approach in the 10 meters per second, and this help design and building help, the commission help by the KIT. So for the ADS system, they have many functions for the energy amplify and monoctinized burning. So now the China focus on the MA burning, so the safety also become very important problem, not only the design and the operation. From the 30 years ago or even more, lots of systems can be studied, has been studied for this purpose. For example, then the heavy metal coolant and gas coolant become a very important choice. This is just gave us several design for this is a gate. It's a tungsten target and with a gas coolant system, and okay, this is EFIT, two kind of EFIT. Okay, so the problem is in fact the basic character of the coolant would decided the whole system. How to say? For example, the density, the thermal property, chemical property, and the radial property could be decided how system is a safety or not, is how to operation, this all kind of things. So compare these two things, we can find that they are quite different basic characteristics. So this is last year IAEA technique meeting gave some comments for these two kind system coolant. So we can see the biggest weak point for the LBE system is the corrosion and toxicity, include chemical and the radio toxicity and this kind of things. But for the gas cooling system, they are quite safety and is no problem for the radioactivity, but they have a very low thermal initial. So this decided by this one. Okay, that's very, very low. So the question is how to avoid this weak point of the gas coolant system and keeping the strong point. So one idea is we can add some granular in the helium. Then we may increase the specific heat capacity. So one simple method is using the fluidized bed. It means to add some very little grains, for example, the 100 micrometers grains into the helium system. But this has been tested. In fact, has been tested. I don't remember exactly, maybe 40 years ago. But the problems, you need very high velocity of the helium and the high pressure. Then another choice comes from the dense granule flow. It's just quite new concept in science. Studied very widely in these 20 years. So, for example, we can choose. It means we can using the very low pressure of the helium. It's normal pressure, and the helium and mixed with the dense granule flow, and this grain we can consider different material to choose. For example, the neutron spectrum. Here, give some example compare with a pure lead, and this is a key effect of the 0.95, and we can see if we using the silicon carbide grains, then we can have this curve, okay, of the fast neutron spectrum. So then we can consider the granule current, the basic property and compare with the water, sodium, the LBE, and the molten salt, and the helium, and the silicon granule. We can see that is the similar to these things and much larger than the helium, and this is the effect copper, the heat conductivity effect heat conductivity. Okay, so it's larger, much larger than the helium, and this is a convection heat transfer coefficient. So this is a different granule and mixed with different gas. Okay, so this is a compare with helium. Then for the granule, the dense granule flow current, we can maybe have some advantage. For example, the low pressure and the high thermal initial for the whole system. And different material of the granules can be optimized for example, for the different purpose. The fast spectrum and low radiotoxicity, small erosion, and chemical toxicity, like this kind of things. So here I give example for the silicon carbide grains and the silicon carbide hexagonal assembly system. So this is conceptual. And we chose the diameter of the silicon carbide granule is 0.5 millimeters, and the helium press just normal pressure. And this is we can choose for example, the MOX fuel and fuel rolled into the fuel assembly using the silicon carbide, and then this is we use the graphite reflector to surround the core, and this is a channel of the current, and then this is some calculation for the density of the power distribution and the different position of the neutron spectrum and the burning calculation for the 116 days. So it's not very, not stable. Yeah, and then the problem is how to control the granule flow, the dense granule flow in the current channel. So we do some numerical simulation and the experiment simulation. We use a glass bed in some hoppers. We design these geometry shapes and compare with the theoretical formula and these two things and like this to get the flow rate, and this is the temperature distribution in the whole system. Yeah. And then this is initially parameters for the list. For example, if we design a system, the total thermal power is 100 megawatts, and the proton beam is the 1 GeV, and the average current is the nearly 5 milliamps. And the effect of the beginning of loading is 0.95. And okay, this whole things. And then for target, the target we also using some idea for the granular. The problem is if we want to have a high average beam in density, is quite difficult things, because if you use the solid target, you need we the surface between the current and the target, but it's limited. And then we can use some rotating the things, or we can use the liquid things. Then it means that we can bring out the heat deposit from the target region, beam target region, to the other place to do the offline the heat exchanger. So now we can see only the windowless design, it can approach in the, for example, 100 microamperes per centimeter square for the average beam density, more than. So for the granule target system, it like this kind of things. The granule flow, the dense granule flow inject from here in all light and okay, thank you, all light from here, and this is things, and we can include target body and heat exchanger, like all these things, and then this is our simulation result compared with some experiment from the up point view. This is designed for the 10 megawatts target. It's 1 GeV and 10 milliamps. The temperature will not beyond the 1,000 degree, and this is a tungsten grains. Okay, this is a simulation result. Okay, and some temperature distribution, fraction of the volume, neutronics, and some estimation for the erosion. And the granule things, we can use a very standard heat exchanger has been used in the industry, mining industry, and the chemical industry things, but it should be how to say co-developed to the the nuclear facility. And this is the grand elevator. It has also have the standard products. And then another very important thing we do begin to the experiments to test the erosion between the tungsten and the silicon carbide. So, but we test in the different do some experiment test in the room temperature to the 1,000 temperature. Then the well is not so much. I can see that. And then that is the granule target test loop design, and it would be finished maybe in this year and begin to test next year. And then the final we become to develop some software, because this granule things know very well exist software to calculate, to estimate whole system. So we need one thing is the radiation transport computational in the stochastic granule and the neutronics analysis, one thing. Another thing is we need to do the how to control the granule flow and do the very mass parallel simulation for the fluid flow, and to analysis the thermal hydraulic. And then this is our test this year in this machine. This machine in the 2 years ago is in the top 5 is rank first in world. And then we do some simulation, do some test for the more than 500 GPU. It means has more than the 200,000 ALU. Okay, compared to the CPU score. And now we got the parallel efficiency nearly the 40%. And we calculate the grains, the number of the granule is the 215 million. Okay, and then thank you for attention.
Thank you very much, speaker. Do we have any questions on the floor? Yes, the gentleman in the center.
I'm afraid to have to tell you that silicon carbide is not stable at 1,000 degrees if there is the least danger of oxidizing agent. We have a long experience of this material in the gas exhaust in the automobile, and it can easily burn.
Oh, yes. Yes, you're right. You know that? Yeah, I know that. So the temperature of the core will not beyond to the the temperature will not larger than the 600 degree. Yeah. Okay. I mean this, yeah, here, this temperature. Yeah.
Any other questions? Jean-Pierre. Yes.
What is the effect on the neutron spectrum of these carbides spheres? I mean, is it not degrading a little bit the spectrum, making it more thermal?
No, it's for example, here is a faster neutron spectrum. This red line is for the carbide, the silicon carbide grains. Yeah.
Because there is a little bit of carbon and things like that, so I'm surprised it does not change the spectrum more than.
Yes. Okay, we calculation more. For example, here in the different position in this core, and this is a different positions of the neutron spectrum. So it would be a little bit soft than the lead, pure lead, or LBE, but okay, I think maybe it's how to say, it's not so soft. Yeah.
And what is the K value that you have?
K value is the 0.95.
Okay,
the beginning
so
of the loading.
So you have an exponential decrease of the flux?
Yes.
So a very non-uniform burning of the minor actinide?
Yes. Our idea is just to put in the, how to say, in assembling just 1 or 2 layers of the metal actinides, and then it's a different.
Okay.
Yeah. Just 1 or 2 lines.
Use the.
It is the center, of the neutron around the target.
Yeah. Okay. Thank you.
Thank you. Yes, Hamid.
I have 2 questions. The first one, I didn't understood how you are cooling the fuel. Is the fuel in your powder also, or is it separated?
It's separated. So the fuel rod, for example, is here, and then this is a cooling channel. In the cooling channel, we mix the helium and the grain of the silicon carbide. Yeah. So it means the heat will be transferred from for example, from this is the fuel of temperature of the fuel of the rod, and then the heat will diffuse from here. This is assembling the silicon carbide assembling, and this is a coolant channel here. Okay, like this kind of things.
Second question is, you said that your granular there is 500 millimeter, the diameter of
yes.
the cores?
Yeah.
0.5, okay.
Yeah.
And these experiments you were running with the tube there, how long was your tube?
Yeah, this is a design.
The experiment, this one?
Yeah, this design, is only, so it's not high, it's the 70 centimeters.
But your experiment then?
This experiment, is
70 centimeters?
Yes, just like this.
Okay.
It's not high.
And you didn't see any stack of the it is flowing normally?
Yeah, it's flowing normally, and the flow rate is quite stable up to now. I don't know.
This is very strange, because we have done those experiments. It blocks by itself, and then it will go back. Because we are designing the same things for the control rods.
Oh, I see. we can discuss later, maybe in detail. I don't know. Okay.
Right. Are there any other pressing questions? Otherwise, we'll go on to the next gentleman. Oh, yes, there is. Sorry.
My name's Ed Pyle. My question is, do you have any long-term tests, flow tests at temperature planned for this? It's kind of an add-on to that. How long have you run it, and do you plan on
up to now, we have known this experiment for a long time running. Yes, just a short time. Yeah, but next year we are commission our test loop. Then next year, beginning of next year, we will begin the long-term test. That.